All right, now that we've talked about reading graphs, we're going to talk about some specific functions. And so we need to create a library. We need to create a place where we have the parent graph or the basic shape that we're going to be studying for quite a while. Okay, so we're going to take a look, and what I'm going to do, instead of me putting a whole bunch of graphs all over the paper, you can do these on your own. I also put a template into our Canvas module, and you can print that out or follow along if you don't have a printer. So first of all, we know that X is the domain and Y is the range, and all of these are functions. So we already know for every X they're going to have one Y value. So what we want to do is we want to take a look at some basic functions. The first one that we're going to look at is what is called the constant function. So I'm going to give you the name of them. I'm going to give you the graph of them, and we're going to talk about whether they're, what the domain is, what the range is, whether they're even, whether they're odd. We're just going to go back through some vocabulary. So a constant function is just that. It's a function that is consistently the same. A constant function might look like the following. Okay? There's a constant function. As you read from left to right, it is always the same value. So a constant function would look like this. F of x equals whatever that y-intercept is. So if you think back to y equals mx plus b, it's whatever that b is. It's a horizontal line. Okay, so let's take a look and identify some of the parts and pieces. Well, let's take a look at the domain. The domain is always your x values. As you read from left to right, we're going to have an x value everywhere along that line. So our domain is the symbol double striked R, or you could write it as all real numbers. Then, after we look at domain, we want to talk about what the range is, because this is a relation, it's a function, it's a relation. It has y values as well. And so as we've been practicing the first half of the chapter, all right, let's follow our y's. What's our y value? Well, we only have one value. Our y value happens to be whatever this value of b is. That's it. So I'm going to put this point in here. It's kind of hard to see. This point is our y-intercept, so it's 0, whatever our b value is. And then, is this function even, odd, or neither? Well, even functions reflect about the y-axis. So this function does reflect about the y-axis and lands on top of itself. So this function would be considered even. I'm going to write this down the first time, but I'm not writing it down again. It's an even function since f of x has y-axis symmetry. Okay, so the next function we're going to look at is what's called the identity function. Here's your x-axis, here's your y-axis. Your identity function says that f of x, which is the same as the y value, equals x. So in other words, when x is 1, y is 1. When x is 2, y is 2. When x is 3, y is 3. When x is negative 1, y is negative 1. The identity function is the line y equals x. So, whoops, I missed the origin a little bit. It should pass right through the origin there. Okay? So again, we're going to look at domain, we're going to look at range, we're going to look at whether it's even, odd, or neither. This pen is running out of ink. Maybe I have another purple one. And if not, I'll switch. This is a little thick, so I might switch from now on. The domain is whatever the x values are. Well, as I read left to right, my line goes on forever. So my domain is all real numbers. The range is your y values. How far from the smallest y value to the largest y values on the graph? Well, you'll notice we go from negative infinity all the way to positive infinity. All real numbers. Is this graph even, odd, or neither? Well, does this graph reflect about the y-axis? No. Does it reflect across the origin? Yes. So this is an odd function. Again, I'm going to write this down once and then not again. Since the function f of x has origin symmetry. So let's keep going. The next function we're going to take a look at, let me give you an x, y. It's a little crooked. So we've done the constant function, we've done the identity function. We're going to do the square function. The square function kind of tells you what we're doing with x. The square function is f of x equals x squared. And some of you already know what that looks like. If you're not sure, you're always allowed to plug in and make a table of values. We could easily do that. Easily do that. If x starts at 0, y is 0. If x is positive 1, 1 squared is 1. If x is positive 2, 2 squared is 4. If x is positive 3, 3 squared is 9. And so this is a parabola. If x is negative 1, we get negative 1 squared is 1. Negative 2 squared is 4. Negative 3 squared is 9. So we end up with this very nice, very symmetric parabola. So feel free to tell yourself it's a parabola. So the purple pen's not working, so I'm going to stick with this blue one. So since it's a parabola, let's take a look at the domain. As we read from left to right, no matter what x value I choose, I'm going to find a point on the graph. No matter what x value I choose, I'm going to find a point on the graph. So as I read from left to right, there's a point on the graph everywhere, so our domain is all real numbers. Our range represents what our y values can be. We always go small to large. So if I start way down here at the opposite of infinity, or what you might think of as negative infinity, I come all the way up. The very first point that shows up is when y is 0. And then I get a value at y is 1, y is 2, y is 3, y is 4. So from here up, I have points on the graph. So y is greater or equal to 0. Or if you prefer, as I do, write it as an interval from 0 to infinity. You can never touch infinity, so infinity is always an open circle, open bracket. Is this function even, odd, or neither? Well, again, since it has y-axis symmetry, it's an even function. Okay, so let's take a look at the next one. All right, so our next function, let's take a look at the cube function. So it kind of already tells you what you're going to do with the x value. It's the cube function, so this would be f of x equals x cubed. And again, feel free to make a table of values, mentally or physically. This is the parent graph. All x cubes will look like this, all third degree. Well, let's start in the middle. If x is 0, 0 cubed is 0. If x is positive 1, 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. 2, 8. 3, 27. I'm not going to count all the way up there. Similarly, if I go negative 1, negative times a negative times a negative is negative 1. Negative 2 would give me negative 8. And negative 3 would give me negative 27. Negative 1, negative 1. Negative 2, negative 8. Negative 3, negative 27. Negative 4, negative 64. Negative 5, negative 125. And when we combine these together, we're going to get this smooth curve that's passing through the origin. So our domain, well, it sure looks like I can either look at the graph, and as I move from left to right, there's a point at every single location. Or ask yourself, can I put a negative number in here and cube it and get an answer? Yes. Even a decimal? Yes. Even a fraction? Yes. Can I put 0 in here and get an answer? Yes. Can I put a positive number in here and get an answer? Yes. So the domain is all real numbers. Or if you prefer, you could say from negative infinity to positive infinity using intervals. How far does this go in the y direction? Well, it sure looks like it goes down forever, and it goes up forever. So the range is also all real numbers, or from negative infinity to positive infinity using intervals. And then, since this does not reflect about the y-axis and land on itself, but it does reflect through the origin, as you can see, for every x, y, it reflects to the opposite of x, opposite of y. This is an odd function. Okay. So let's look at the next one. Let's see, we've done square, we've done cube. We could do square root and cube root. And these are the basis for most functions you'll see as you start off. Let's see, since we did the square, we'll come over here and we'll do the square root function. And again, you can write all these out. They're all in your book. Okay, since we did the square function, the next one we'll look at is the square root function. So again, it tells you what you're probably going to be doing with your variable. So this would be f of x equals the square root of x. And again, when in doubt, write it out. Make a table of values. Okay? So if you're not sure, make a table of values. I always like to start at the origin. Square root of 0, 0. Square root of 1, 1. You could do the square root of 2, but since you're the one choosing values, just go straight to perfect squares. Square root of 4, 2. Square root of 9, 3. 0, 0. When x is 1, our output is 1. But I've got to go all the way to the number 4 before we go up to the number 2. Because the square root of 4 is 2. Then we've got to come all the way out to 9 before we barely go up to the number 3. Then we'd have to go all the way out to 25, or I'm so sorry, 16, before we could go up to the number 4. What about the square root of negative 1? Well, we can't take the square root of a negative and get a real number. If you remember, those are what we call imaginary. And imaginary numbers are not real. They're part of a different number system, and so we can never have a negative in a square root. So the square root is only part of a parabola, if you want to think of it that way. It has everything to do with a square root and a square. So let's look at our domain. Domain is what your x's are. Well, if I come down here to the negatives, there's not a point down here on my graph where an x is negative. So as I read from left to right, the first graph point that shows up is when x is 0. And then you'll notice that no matter what I choose for x, I have a point on the graph. So as I move, I end up with points for x, anything to the right of 0, including 0. So you could say x is greater or equal to 0. Or you could use the interval that says start at 0 inclusive and go to infinity. Similarly, the range does the same thing. You'll notice our range value can also not be negative, right? There's no negatives. There's not a single point when the y value is negative. The y values start at 0, and then our y values keep going up from there. Or from 0 to infinity. And because this graph does not reflect over the y value and land on itself, it's not over the y-axis, so it's not even. There are no pieces that are in the opposite quadrant through the origin, so it's not odd. So it's not even, it's not odd, it's neither one. Neither even nor odd. Neither one. Okay? So the next function we're going to take a look at is what's called the cubed root, because we just did the cube function. So let's look at the cubed root function. So it says y equals the cubed root of x. So again, we're looking for perfect cubes. We're looking to have this radicand, this number on the inside, a perfect cube. So I'm going to start with 0. Cubed root of 0, 0. Cubed root of positive 1, positive 1. When x is 1, y is 1. Cubed root of 2, kind of hard to take. 3, 4. It takes all the way until I get to 8, when the cubed root of 8 would be 2 times 2 times 2. Then I have to go all the way out to 27 before I get 3 times 3 times 3. Then I'd have to go all the way to 64 before I get to 4. All the way to 125 before I get to 5. So here's 1, 1. But now I have to go all the way out here to 8. 2, 3, 4, 5, 6, 7, 8. Before I can barely move up to the number 2. Then I have to come all the way out, not drawn to scale, all the way out to 27 before I can get to the number 3. So this part looks like this. But now when I take the cubed root of -1, a negative times a negative times a negative is negative. So I can have a cubed root of -1. I can have a cubed root of -8. I can have a cubed root of -27. All the way out here to -8 before I get to -2. All the way, am I still on the board? All the way out here to -27 before I get to -3. Okay, so a cubed root looks like this. It's the inverse of a cube root. So, doing the same thing, our domain, how far left and right will this graph go? It will go forever. It will be all real numbers, or negative to positive infinity. Our range, well, it looks like our range values keep going in the negative and the positive direction. Our range value is also all real numbers. And since it reflects through the origin, by definition, every x, y reflected to the opposite of x, opposite of y, it's an odd function. We have a couple left. Let's take a look at the reciprocal function, absolute value function, and the greatest integer function. All right. These are all the parent graphs. These graphs are quite helpful to know what they look like so that as we go through equations, we'll know what they're supposed to resemble, because everybody resembles their parents, biological parents. All right, let's take a look at these last few. And again, I always recommend making a table of values or doing it mentally. We're going to look at the absolute value function. So again, the name pretty much tells you what you're going to be doing. F of x equals absolute value of x. Again, you are always allowed to make an XY chart if that helps you. Absolute value of 0, 0. Absolute value of 1, 1. Absolute value of 2, 2. 3, 3. Absolute value -1, +1. Absolute value -2, +2. Absolute value -3, +3. So we end up with this lovely V graph. We end up with the identity and the opposite of the identity. Where when x was 1, y was 1. When x was 2, y was 2. Same thing in the negatives. So again, you can ask yourself, either looking at the equation, can I substitute a negative in here and get an answer? Yes. Can I substitute 0? Yes. Can I substitute positive and get an answer? Yes. Or you can look at the graph. As I go from left to right, no matter where I am, there's always a point that's on the graph. So the domain is all real numbers. Or, if you prefer, from negative infinity all the way to positive infinity. Our range is our y values. So, looking at our graph, our lowest y value, we have nothing down here is on the graph. Nothing, 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 nothing. Stop. The first point that shows up on the graph is y is 0. And then you'll notice no matter what, I end up with a point on the graph for every single positive value. Or you could say it's the interval from 0 to infinity. I will take either answer, either one. Okay. And then because it has y-axis symmetry, this is an even function. So you're kind of getting the idea. All of these are similar to each other. All right, let's take a look at the reciprocal graph. And then we're going to spend half of chapter 3 looking at this graph. All right, so we will examine it again later. So we want to show you what the parent graph looks like now. Here's our domain. Here's our range. We're taking a look at the reciprocal function. So the reciprocal of x, well, you all learned the reciprocals when you flip it over, quote unquote. So the reciprocal of x would be 1 over x. All right, well, we notice we have a fraction, so there's a few things we have to keep in mind. All right, think about the denominator. Of course, you can make a table of values. If I start with 0, if I substitute 0 in, we can never have 0 in a denominator. So this is undefined, cannot divide by 0. If I substitute positive 1, 1 divided by 1, 1. If I substitute in 2, I get 1 divided by 2. If I substitute in 3, I get 1 divided by 3. So you'll notice that if I substitute in 2, I get a half. If I substitute in 3, I get a third. 4, I get a fourth. I'm getting smaller and smaller and smaller and smaller. What if I substitute in 1/2? Well, the reciprocal of 1/2 is 2. What if I substitute 1/10? The reciprocal would be getting larger. So at x is a half, I get 2. As x is 1/10, I get 10. So I end up with this graph that never touches the y-axis, never touches the x-axis. Those act as asymptotes. And it's in the first quadrant. And then look what happens if we substitute negatives in. The reciprocal of 1 over -1, -1. Reciprocal of -2, -1/2. We have the same thing occurring. Reciprocal of -3, -1/3. So we actually get this reflection. So it ends up being in the first and the third quadrants for the parent graph. So let's start. Now you guys, we've done domains of fractions before. We did this in chapter 2 early on. Okay? We looked at domains. So we can also look and say, well, I can see that my x values are negative, negative, negative. At 0, however, it's undefined. So x cannot be 0, but it looks like it could be anything negative, anything positive. So I would say it's all real numbers except for 0. Similarly, if we look at all our y values, our y values, well, we have negative y values, can't be 0, and we have positive y values. So y cannot be 0 either. And then by definition, it reflects through the origin, so this is an odd function. And then the last one we want to take a look at, we use a lot to describe some functions in calculus, and this is what's called the greatest integer function. The greatest integer function. And your author, your book, chooses, let me see how they chose, right? They choose to write it as f of x equals, and they put int to stand for integer. And I'm going to suggest you write down these words, okay? Because what you want to do is you want to round down. We want the greatest integer less than or equal to whatever number I choose, x. And an integer is a positive or negative whole number. So no fractions, no decimals. I would suggest you write that down. Positive or negative whole numbers are integers, and 0. So we are for sure going to make a table of values. I'm going to leave my spot up here for domain. I'm going to leave my space for range. And then we'll figure out if it's even, odd, or neither after we graph it. But I definitely want to do a table of values with you guys. And I definitely want to do a large table of values. Okay? You may not need to write these down, but I want to kind of make it a point. All right. I'm going to start with 0. If I substitute in 0, what's the greatest integer less than or equal to 0? Well, since integers are positive or negative whole numbers are 0, our answer is 0. Okay? So at 0, we get 0. Now, I'm going to do this on purpose. Let's say I give you 1/10. I want the largest integer less than or equal to 1/10. That would also be 0. Let's say I go to 1/2. What's the largest whole number, or 0, less than or equal to 1/2. I get 0 again. Let's say I go to 0.5. Oh, that is a half. Let's say I go to 0.6, 6/10. I'm going to round down to 0. Let's say I go to 0.9. Greatest number less than or equal to that greatest integer is 0. Let's say I go to the number 1. What's the greatest integer less than or equal to 1? 1. So what happens is between 0 and 1, your answer is always 0. And then when we get to the number 1, our output is 1. So it doesn't touch here, but it jumps. Then between 1, 1.2, largest integer less than or equal to 1.2, 1. 1.8, 1. And it doesn't change until I get to the number 2. So everything between 1 and 2 is going to round down to the number 1. And then at 2, it jumps to 2. And then it stays like that until we get to the number 3. And once I get 2.1, 2.2, 2.3, 2.4, all of those output is 2 until I get to the number 3. Then it jumps to the number 3. Well, if I keep that same pattern up, if I'm at negative 0.9, it rounds down to negative 1. Negative half rounds down to negative 1. Negative 1 rounds down to negative 1. Or follow this pattern. It's going to be open, closed. And then at negative 2, it's going to be open, closed. Okay? And so this is what we call a step function. This is called a step function. We see these a lot in calculus because it describes taking steps. So our domain, well, it sure looks like we could put any negative number in here, any 0, any positive number in here for x. So our domain, even if I read across, as soon as I get to that open circle, it shows up right here. So my domain is all real numbers. But the range is just these step values. The range are just these y values. The range are just the integers. And then although this looks odd, it's not. Because you'll notice that this identical piece, it's absolutely identical. We did not switch the x and the y value. So it is neither even nor odd. Okay? So what I'd like you to do is get familiar with these first. And then next time we're going to take a look at what are called piecewise functions. So I'm going to do a second video. It'll be a lot shorter, but it'll be piecewise.